Hi, we're here with EECS 203, and our talk today is on proofs by contradiction. So we're going to begin with a brief definition. A proof by contradiction proves the truth of a proposition by demonstrating that a contradiction occurs if the statement is false. Now, there are a couple of very basic steps that one must perform in a proof by contradiction. The first being that you need to begin by assuming the negation of the proposition. Basically, you begin by assuming the negative of the premise, and you prove that it's actually true when you reach a contradiction. Now, these are very basic steps because, as you'll see in the next couple examples, you have to go through several different methods to actually reach a contradiction, and it's very dependent on the actual problem. So, moving into our first example, we're going to prove that there is no greatest even integer. So we're going to begin by assuming that there is a greatest even integer. And let's call this greatest integer capital N. So then we have that for all even integers n, capital N is greater than or equal to lowercase n. Now, let's have a new variable that we're going to call m be equal to capital N plus 2. We know that m is even because it is the sum of two even integers. Now, since m is equal to n plus 2, we see that m is greater than n. Therefore, m is greater than the greatest even integer. This is a contradiction. So therefore, we see that there is no greatest even integer. Moving on to our next example, we're going to prove that the product xy of a rational number x and an irrational y is irrational. So before we move into the proof, I'd like to define what it means to be rational and irrational, just so everyone's on the same page. Irrational, often written Q, is any number that can be written as the quotient of two integers. So m and n are elements of Z. And an irrational is any x that is not rational. So, moving into the proof, we're going to begin by assuming that xy is rational. So by definition, this means that we have xy equal to m over n, where m and n are integers. Since by hypothesis x is rational, we have that x is equal to a over b, where a and b are also integers. So plugging this back into our original equation, we have that a over b times y is equal to m over n, which you can simplify to say that y is equal to mb over na. Now, the product of integers is an integer. So mb and na are integers. This demonstrates that y is the quotient of two integers. Which implies that y is rational. This is a contradiction, since in our hypothesis we say that y is irrational. So therefore, we see that the product xy must be irrational. As you can see from our examples, there's a couple basic methods to prove a proof by contradiction. You always begin by assuming that the premise is the negation of the premise. And from there, you take a number of steps to reach a contradiction involving your hypotheses that would lead you to believe that the premise must in fact be true, therefore proving the theorem or proposition. I hope this has helped you learn proofs by contradiction. Thank you for watching.